Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel where I talk about everything that I want to about science and math. Today, this is physical science, and we are talking about nuclear chemistry. Last time, if you watched the last video, we talked about atoms and how atoms are made out of protons and neutrons in the nucleus and electrons around in orbitals and clouds, we learned. Well, I told you that in the nucleus of the atom, protons are what makes the atom have its identity. So like if it has 6 protons, it's carbon. If it's got 1, it's hydrogen. 2, it's helium. But the number of neutrons, there can be more or less. And that often when there's too many neutrons, it's unstable and it becomes radioactive, like carbon-14 with 6 protons and the rest neutrons is a radioisotope, where carbon-12 with 6 protons and 6 neutrons is not. So that's why this chapter is next and why it segues into it. So it's called different isotopes, the different numbers of neutrons that are different types of a element. Now, on the periodic table, each little square represents an element. There's a whole number. The whole number is the number of protons. There's also a decimal number. The decimal number is the mass in atomic mass units, and where it comes from is they take all the different isotopes of that element and they average it to be the average mass. There's no element that has that mass, because the masses are actually in whole numbers, because it adds up the number of protons and the neutrons to get the mass. And they don't split. They're whole numbers. But they take the different isotopes and they multiply them by their percent abundance. So like there's mostly carbon-12, but a little bit of carbon-14. They multiply them by their percents and then add them up. And that's something that if you take chemistry, you'll learn how to do. Okay, now, so we learned a long time ago that opposites attract and likes repel. So 2 positive charges will repel each other, where a positive and a negative attract. And we talked about that's why water is a sticky molecule, because it has a positive end and a negative end and they stick together. Well, that begs the question, how does a nucleus stick together? It's all positive. Why aren't those positives repelling and the nucleus flying apart? Well, according to people a lot smarter than me that understand this more than I do, there is a force. And from what I understand, we don't know everything about it. In fact, maybe not much at all about it, but it is a force that holds those positive particles together in the nucleus, even though naturally they want to fly apart. And they said that it must be very strong and it must act over a very short distance. So it's called the strong force. It's like, who is in charge of naming that? But that's what it is. And when I first started teaching this decades ago, we're not going to talk about how many, there was less known about it than there is now. I read some current research, and because when I first started teaching this, it was like, there's nothing known about it except it holds it together and it must be strong. But now some of the new research, more is coming out. So you're welcome to read it and learn more about it, but that's about it. Okay. Let's see, attractor, repulsion, radioactivity. Okay. When an element is radioactive, what does that mean? It means that it is giving off something. And you can sort of imagine if it's radioactive, you can see little lines coming out from it. Well, what it gives off could be different things. There are different kinds of particles. There are alpha particles, which we talked about last time, are positively charged. There's beta particles that are negatively charged. There's gamma rays that don't have any charge at all and they're just radiation. They're just wavelengths. This is here comes a gamma ray. Woo! It's high energy electromagnetic radiation. It's like light, but like turbo light. And I don't know if it gives people superpowers like the Hulk or not, but it's out there. Gamma radiation's a thing. It's real. Let's see. So the other thing is nuclei can become so big and with so many neutrons that they're more likely to be unstable. So like uranium is the largest naturally occurring element, and there are no stable isotopes of it. They're all radioactive. It's huge, it's got lots of neutrons, and it is radioactive. Now, these radioisotopes, these radioactive elements, can give off more than one thing. It can be giving off, and the other thing is, the radioisotopes, like uranium, are so big that they are radioactive and they can spontaneously break apart. They're so big and so unstable, they'll break apart. And, well, uranium, okay, there's some different things going on here. One is that uranium can spontaneously give off radiation. It is unstable, so it could give off gamma rays or some other kinds of radiation. Another thing is, when they're very big like this, it's easy for them to split, which is nuclear fission. See, kids always get confused which one's fission, which one's fusion. And nuclear fission is where the atoms split. So I tell them to imagine a fish, imagine a knife, and you're cutting it, you're fish, and it's fission. So it's splitting the atom. So uranium can break apart into two different elements. So that old idea of the alchemist trying to make one element change into another, we can actually do it now through nuclear fission. We can split the atom. Now, when this is done, tremendous amounts of energy are given off. So you find it in nuclear bombs, you find it in nuclear power plants, you find this in the sun and other stars where because of E equals mc squared, there is a relationship between mass and energy. And when these nuclear things happen, some of that mass gets turned into energy. So great amounts of energy can be given off. Now, I told you that fission is splitting the atom, and that causes energy release. But also fusion, taking two little atoms and shoving them together to make a new, bigger element, also gives off energy. And where we see that is in the sun and other stars. Hydrogen, number one, can be fused by the tremendous gravity of the sun into helium. And when that happens, because of E equals mc squared, tremendous energy is given off in the sunshine. So now when you're a parent and your kid says, "Mommy, Daddy, why does the sun shine?" You can say, because of nuclear fusion. So you're fusing it together. So imagine fusion, you're putting it all together. I told you about alpha, beta, gamma. There can also be just neutrons given off in radioactivity. Are they good? You can look at the different kind of particles, alpha, beta, and gamma. Now, half-life. Okay. If you have a whole sample, say you've got a sample of carbon-14, then in a certain amount of time, half of it will turn into carbon-12. Half of it will decay, will undergo nuclear radiation, and decay and become carbon-12. The time it takes to do that, theoretically, is always the same. So like in lab, one of the things you're going to do is, I think you do pennies in your lab this week, but you can look in the comments for it. But there's different ways to do this. Usually what I do with my students is I have pennies. I make them put them all on heads and then shake the box. And half of them turn over. You take those out and then you shake it again and half of them turn over to the other side. Take those out, take those out, take those out. And it makes a graph, a really nice, pretty half-line graph. Theoretically, the way this is supposed to work is if you have a sample, it's in its half-life, the time period that it takes for half of the isotopes to decay, then if that time passes, like with carbon, I think it's like 5,730 years. I might be off, but that's just the number that came to mind, and it's late. But after that amount of time, half of the carbon would have decayed. If you give it that time again, of what's left, half will decay. If you give it that time, that's, again, half of what's left will decay. Half always decays until eventually you would end up with none. All right? Now, research I've read, though, said that, when they discovered all of this, they thought it was like clockwork. And in fact, they made nuclear clocks that were going to be better than any other clock, because they thought this was absolutely set in stone, that the isotopes exactly obeyed the idea of half-life. But recent research says, not so much, that it might not be as constant as they thought it was. So go read that research. It's interesting. It's interesting. The longer I have been teaching science and reading science and keeping up on it, it's so interesting, all these things that like I taught absolutely decades ago. We won't talk about how many of them now. It's like, maybe not. So that's the great thing about science, is we're always learning, we're always discovering, and we're not afraid to question established things. Today they might say, absolutely, this is true, this is false, and give it a little bit of time. Sometimes with science, it changes. I've seen it happen over and over again. Okay, so it talks about in your book, and whatever book you're following with, but if you're doing this as a class, it talks about carbon dating. It talks about uranium dating, and that's where they take a sample and they look to see how much carbon-14 is in it, and then they estimate its age based on this idea of half-life. Now, there's been some problems with this, in addition to half-lives not being as stable as we thought they were. Another problem is, when we very first started doing this, we kept getting carbon-14 in samples that we thought were so old they should have none, if that makes sense. There should be none in it. But they said, oh, it's just contamination. I'm a living thing and other living things are around. Somebody had a sandwich. There's got to be some contamination is where this came from. But now we have gotten so good with our science, we can have a sample with no contamination. We can control the actual atoms that are there, and there's still too much carbon-14. So either our dating isn't as good as we thought it was, which I've already told you it seems to be off, or maybe things aren't as old as we thought they were. We don't know. So just interesting. Once again, we don't know as much as we think we do. Okay, now, how can radiation be detected? One way is a Geiger counter. It's this little machine, and it clicks as it gets near radiation. Click, 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 click. Now, my old school didn't have one when I taught public school. But another teacher that I taught with, her old school did. And one time, one of the other chemistry teachers had the Geiger counter, and he had it out showing all the kids, and he was walking around the class with it on, and it was going tick, 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 because there's always background radiation. And he came up to one kid, and it just went tick, 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 tick. Well, it turns out she had cancer and was undergoing radiation therapy, and was so embarrassed that the other kids found out she was radioactive. So at my new school, where I teach public school, we were digging through the stockroom looking for hot plates last week, and there was a Geiger counter in there, and I was like, oh, I can't wait to show it to my students. But I thought, but I'm not walking around with it. I'm not going to embarrass anybody if they're radioactive. So anyway, and I don't think it was because she was a superhero with radiation. She had cancer. Another way to detect radiation is cloud chambers, bubble changers, electroscopes. There's a lot of ways. One way that is really common is a lot of places where you work, where there could be radiation, they make you wear a badge, and if you have been exposed to radiation, the badge turns colors, so that way a coworker can alert you. Now, what if you get radiation on you? What do? They send you to a shower and wash off, because a lot of radiation can be stopped by your skin, and so you get it off. You really want to make sure you don't eat or drink any of the radiation. You want it off of you on the outside. So they strip you down, get rid of your clothes, give you something new to wear, wash you off. Now, when I used to be a TA, a lab assistant in college, and we were doing a lab with radioisotopes, and we had these little They just look like little cardboard, little bitty oatmeal canisters is what it looked like. Okay, and they had where you could activate it and it gave off alpha particles. So we had these little things and everybody was doing their lab and they tested the alpha particles like they were supposed to. And I was the teacher and I had told everybody, you know, what to do and how to be safe and everything. Well, at the end, they were supposed to come up and put their radioisotopes in the thing to be disposed of safely. And I was sitting there, you know, near the thing. Well, some kid walked up to me and said, here. And I held up my hand, not even thinking. They took their radioisotopes, instead of putting it in my hand, they poured it in my hand. So I had radiation all down my hand and it felt hot. So I went and washed my arm, but it still felt hot. But so far it's okay. It hasn't turned green, hasn't fallen off, hasn't gotten cancer, and that was decades ago. But I still don't have superpowers. I thought if I got dumped in radiation, I'd be like She-Hulk or something, get super strong. But no superpowers, even after having a kid dump radiation all over my arm. So anyway, I was just so irritated because they didn't listen to me. Now, remember how I said when the teacher was walking around the room that the Geiger cow would go click, click, click from background radiation? What is background radiation? What does that mean? We always have radiation around us because it comes from the sun. So there's always radiation. And people who fly are up higher and they have less atmosphere to protect them. They get more exposure to radiation and they're more likely to get bad things from radiation like cancer. So they try to limit their exposure and people in the airline industry try to watch out for that. But they get more exposure with flight. So anyway, so background radiation is always there. And our atmosphere, our ozone, our atmosphere helps protect us from it. So if you go way high up, where there's not so much protection, it can cause more problems. Now, I talked about that there's nuclear fusion and nuclear fission. Fission is splitting the atom. So the bombs, like what was dropped in World War II, those are nuclear fission bombs where atoms are split using E equals mc squared to convert mass into energy to make a big bomb. Now, it turns out there's a few little pointers about that. One is it won't become a bomb unless you have enough stuff. Enough stuff has to have a fancy science name, so it's called critical mass, the critical mass. The other thing is it causes a chain reaction. So I want you to do a lab this week where you model chain reactions with dominoes. You'll do one where the dominoes are all lined up regular, where one domino hits down the next one like that. And that would not be a chain reaction. That's just one hitting down another one. But to model a chain reaction, one domino needs to be set up where it can hit down 2, and 2 knock down 4, and 4 knock down 8. And then 1 is causing it to grow, and it's the chain reaction. Now, when they very first made the atomic bomb, there were scientists who thought that there'd be no stopping it. They were going to blow up the whole world. But they did it anyway. That's how bad they thought Hitler and the Nazis were, and how bad they wanted to defeat him. And there were some of the scientists thought that when they did this, it would make such a big bomb that it would cause the oxygen. Our atmosphere is 20% oxygen. They thought that the oxygen would catch on fire and that it would burn the whole world up. And they did it anyway. That's pretty shocking, isn't it? But it didn't. It didn't blow the world up. Newsflash. And it didn't catch the oxygen on fire. It made the mushroom cloud and then it dies out. Chain reactions, temperature fusion, fusion in the sun. We already talked about that. Okay, now what about nuclear isotopes in medicine? I said that the girl had cancer, was undergoing radiation therapy. Weirdly, radiation can cause and cure cancer. Isn't that odd? I don't understand it completely. There's doctors who do. I have a friend who's a cancer doctor who would understand that, but I'm not the one. But you can read more about it. The other thing is nuclear isotopes can be used as a tracing mechanism. So like if they need to see inside of you how certain things are flowing, they'll shoot you with a radioisotope, usually of iodine, I think. And then it shows up on this x-ray machine and you can see it. So like, so they can see how things trace through, but they'll even use radioisotopes to trace like how water and minerals flow through a plant and things like that. So they can be used as tracers. Also, it can nuclear radiation can be used to help preserve food. They'll take food and they'll zap it with radiation. It kills all the germs and bacteria on it, and then they send it off to us to eat, but the radiation is like light. It's gone. It's like once you turn off the light's gone. That radiation's gone. It's not in the food anymore, and it preserves it a lot longer. It was a little controversial back in the 90s when I first started teaching, but now I think most of our produce is irradiated because it does not spoil like it used to. Produce used to spoil much faster than it does now. Now, those potatoes will just be there forever until they start growing potato plants out of their eyes, where they used to get bad a lot quicker. Tomatoes used to get bad quicker, all of those things. So they use it to treat cancer. I told you that. There was something else I was going to tell you about radiation, isotope tracing. I don't know. That's all the book has, but it seems like there was something else I was going to tell you about radiation, but I forgot it. So, well, science is great. Come back. We'll watch another video. Like, share, subscribe.